Chapter 15, Part 2, Packaging. Packaging of instruments should be performed according to standards for packaging products for sterilization. Appropriate packaging materials must be selected based on recommendations of the sterilizer manufacturer. ETO sterilization is compatible with a variety of packaging materials, including paper, plastic, or tie-back peel pouches, approved fabric wrappers, medical crepe paper, polypropylene, and most container systems. Note: aluminum foil, cellophane, nylon films, polyester, PVC plastic films, and styrofoam should not be used. Loading and unloading ethylene oxide sterilizers. ETO sterilizers must be properly loaded for effective sterilization. Overloading impedes proper air removal, load humidification, sterilant penetration, and aeration. Items should be arranged to avoid contact with chamber walls. Pouches should be placed on edge in the wire baskets. Stacking one package on another should be avoided. Aeration, because ETO can be absorbed by many materials, aeration is required to remove ETO residual gases before instruments and packaging can be safely handled by healthcare workers or used for patient procedures. When the exposure cycle ends, one or more vacuum pulses remove ETO from the chamber. The aeration phase then takes place as a warm air circulates through the chamber to remove residuals from instruments. Minimum general recommendations for aeration are 8 hours at 140 degrees Fahrenheit or 60 degrees Celsius, and 12 hours at 122 degrees Fahrenheit or 50 degrees Celsius. The rate of aeration is dependent upon many factors, including the nature of the materials used to construct the device. Therefore, the manufacturer of the medical device must provide recommendations for appropriate aeration times and temperatures. Sterilizer performance monitors. An ETO sterilizer should be monitored with physical, chemical, and biological indicators. While none of these provide conclusive evidence of device sterility by themselves, they provide a high degree of sterility assurance when used in combination. Physical monitors, including operating pressure gauges, temperature control measurement devices, timing recorders, and humidity sensors. Charts, tapes, and graphs detailing the measurements made by physical monitors must be carefully examined before instruments are removed from the sterilizer. Chemical monitoring. External chemical indicators, CIs, should be used on the outside of every instrument package to demonstrate that each pack has been processed. Internal CIs should be used inside every package to measure whether the sterilant has penetrated the packaging. Biological monitoring. Biological indicators, BIs, are the most accepted means for providing quality assurance for ETO sterilization. See Figure 15.8. The microorganism of choice for ETO is the Bacillus atrophaeus spore. Biological monitoring is required for each cycle run in an ETO sterilizer. Follow sterilizer's manufacturer's instructions for use for proper biological indicator placement. Hydrogen peroxide systems. Several types of low temperature systems use hydrogen peroxide as a sterilant. While the systems operate similarly, there are some key differences in the types of systems. Hydrogen peroxide gas plasma. Background. The more recent low temperature sterilization technologies cleared by the FDA are considered oxidative process. This includes hydrogen peroxide gas plasma. This method is popular due to its safety, relative ETO, and its rapid cycle times that allow faster turnaround of medical devices. The process uses low temperature hydrogen peroxide gas plasma for rapid inactivation of microorganisms. The byproducts of the cycle, water vapor and oxygen, are non-toxic, eliminating the need for a lengthy aeration time. Hydrogen peroxide is a highly effective sterilant that sterilizes by oxidation of key cellular components. Plasma is a state of matter distinguishable from a solid, liquid, or gas. Gas plasmas are highly ionized gases. Efficacy. Hydrogen peroxide gas plasma using a hydrogen peroxide solution ranging from 59% to 95% for the sterilization cycle is proven effective at killing microorganisms. Laboratory tests have demonstrated that the systems destroy a broad spectrum of microorganisms, including gram-negative and gram-positive vegetative bacteria and microbacteria, yeasts, fungi, lipophilic viruses, and hydrophilic viruses, and highly resistant aerobic and anaerobic bacterial spores. Penetration. Hydrogen peroxide gas plasma sterilizers use deep vacuums, multiple pulse additions of the sterilant, and increased concentrations. These systems can sterilize a wide range of instruments, including some single-channel flexible endoscopes, cameras, rigid endoscopes, light cords, batteries, and power drills. Guidelines have been developed for lumen diameter and length to ensure adequate penetration and efficacy for various cycle parameters. Newer generations of hydrogen peroxide gas plasma sterilizers utilize a higher concentration of hydrogen peroxide, up to 95%, to shorten exposure time and lessen human restrictions. There are still some restrictions involving size, length, and number of lumens, and on the type of material and number of instruments per cycle. As always, users should closely follow the instrument and sterilizer's manufacturer's instructions and recommendations. Types of hydrogen peroxide gas plasma systems. There are several types of hydrogen peroxide gas plasma sterilizers available, ranging from compact systems with 28 to 38 minute processing times to large capacity systems with 75-minute cycle times. Different modules have different cycle times, load capacities, and capabilities for processing instruments. See figure 15.9 for an example of hydrogen peroxide gas plasma systems. Sterilization cycle and process parameters. The phases of hydrogen peroxide gas plasma include vacuum. The load is heated while the vacuum system removes any remaining water as it evaporates. Air is removed from the chamber and packages until the pressure is reduced to below atmospheric pressure. Injection. Once the correct pressure has been reached, a pre-measured amount of concentrated hydrogen peroxide is pumped from a cassette into the vaporizer bowl and then vaporized into the chamber. Diffusion. The diffusion stage drives hydrogen peroxide vapor into the small crevices and lumens of the device. The chamber returns to atmospheric pressure to accomplish this. Plasma. A vacuum that decreases the pressure and radio frequency, RF. Energy is radiated within the chamber from an electrode screen. The radio frequency energy ionizes in the hydrogen peroxide, creating hydrogen peroxide gas plasma. The injection and plasma phases are repeated a second time. Vent. At the end of the second plasma sequence, the radio frequency is turned off. Air is then vented into the chamber through bacterial high efficiency particulate air filters, or HEPA, HEPA, and returning it to its atmospheric pressure. The process byproducts are only water, vapor, and oxygen. Aeration is not required, and instruments can be used immediately following the 24 to 75 minute sterilization cycle. Operators should demonstrate competency in all parameters of hydrogen peroxide gas plasma sterilization. See figure 1510 for an example of hydrogen peroxide gas plasma sterilization process parameters. That is at the top of page 330. Safety. Concentrated hydrogen peroxide liquid can irritate skin and, like other oxidants, is damaging to the eyes if direct contact occurs. In the vapor phase, concentrated hydrogen peroxide is irritating to the eyes, nose, throat, and lungs. However, a number of safeguards built into the hydrogen peroxide sterilizers are designed to minimize the likelihood of the personnel contacting hydrogen peroxide in either the liquid or vapor phase. The hydrogen peroxide is packaged in sealed cassettes, see figure 1511, containing chemical leak indicators on each side of the package. These change from yellow or white to red when exposed to liquid or vapor hydrogen peroxide. The leak indicator is visible through a clear plastic overlap to protect the personal protective handling the cassette. Once the cassette has been placed in the sterilizer, it is automatically advanced by the machine, eliminating any danger of exposure to liquid hydrogen peroxide through handling of the cassette. After 5 sterilization cycles, the cassette is automatically ejected into a collection box for safe disposal. To minimize the likelihood of exposure to hydrogen peroxide when removing items from a canceled cycle, CS technicians should always wear vinyl, PVC, or nitrile gloves, never latex. As with any chemical uses for sterilization, healthcare workers should consult the safety data sheets and follow all manufacturers' recommendations and departmental procedures. To minimize hydrogen peroxide risks, employees should be instructed about the following: hazards of hydrogen peroxide, storage, handling, and disposal of hydrogen peroxide cassettes, handling canceled cycles, applicable OSHA standards, the use of PPE, applicable SDS, safety data sheets, and recommendations for routine maintenance of sterilization equipment. Exposure monitoring. Monitoring of the area around the system during operation should be conducted according to the manufacturer's instructions for use and established guidelines. Materials compatibility. Hydrogen peroxide gas plasma sterilization is compatible with a wide variety of materials found in medical devices and surgical instruments, including some flexible endoscopes, semi-rigid ureteroscopes, and cameras, light cords, batteries, power drills, rigiscopes, and more. Many items processed in the high temperature sterilization system, such as a stainless steel instruments, are also compatible with hydrogen peroxide gas plasma. However, hydrogen peroxide gas plasma is not compatible with the following: liquids and powders, any material that absorbs liquids, and items that contain cellulose such as cotton, paper, or cardboard, linen, huck towels, gauze sponges, and any other item containing wood pulp. Manufacturers of newer low-temperature sterilization technologies, such as hydrogen peroxide, have active device testing programs. These involve cooperative testing with the device manufacturer to evaluate sterilization efficacy and materials compatibility. If hospital personnel have a question about the compatibility of a device with a specific sterilization process, the product manufacturer should be contacted. Packaging. Packaging materials can affect the penetration of hydrogen peroxide. Packaging materials used in the sterilizers should be designed to optimize diffusion. Packaging materials used in sterilizers should be designed to optimize diffusion of the hydrogen peroxide and not interfere with the RF energy, radio frequency energy, or absorb hydrogen peroxide. Trays and container systems from the sterilizer manufacturer and Tyvek pouches are compatible. Check with tray and sterilizer manufacturers before purchase and use of containers. Cellulose containing packaging materials such as paper or plastic pouches, cellulose-based disposable wrappers, and muslin wraps should not be used with hydrogen peroxide gas plasma sterilizers because they absorb the peroxide and inhibit effective penetration. Loading hydrogen peroxide gas plasma sterilizers. As with other low temperature sterilizers, hydrogen peroxide gas plasma sterilizers must be properly loaded for effective sterilization. If the available amount of hydrogen peroxide is reduced because it reacts or is absorbed before reaching all surfaces, a sterilization failure could occur. Therefore, the chamber should not be overloaded. See figure 15.2. Excess moisture remaining on devices can cause the cycle to abort. Consult the manufacturer's instructions for use for suggested drying methods. Sterilizer performance monitors. Hydrogen peroxide gas plasma sterilizers should be monitored with physical, chemical, and biological indicators. Their sterilizers performance monitors include physical monitors. Hydrogen peroxide plasma sterilizers operate on a fixed automatic cycle by a microprocessor. All critical parameters are monitored during the operation of the cycle, and a printed record documenting the process parameters is provided at the end of each cycle. If any process parameter does not meet established acceptable limits, the cycle will be canceled and the printed record will indicate the reason for the cancellation. Chemical monitoring. External CIs, chemical indicators, should be used on the outside of every instrument package to determine whether exposure to hydrogen peroxide gas plasma was present. Internal chemical indicators should also be used to demonstrate exposure to hydrogen peroxide. Internal chemical indicators should be placed at a challenging location inside the pack. Biological indicators are the microorganism of choice for hydrogen peroxide gas plasma. Biological indicator is the Geobacillus pterothermophilus spore. AORN, the Association for Perioperative Nurses guidelines, recommend that biological indicators should be performed at least daily, preferably with each load. See figure 15.13 for an example. Follow the sterilizer manufacturer's instructions for use for proper biological indicator placement.